In this video, we're going to talk about the row space of a matrix. Okay, so I want to begin with the definition. If A is an m by n matrix, the row space of A is the set of all linear combinations of the rows of A. So another way to say the set of all linear combinations is we can say the span. So the row space of A is the span of the rows. And the notation that we're going to use to refer to row spaces, we'll write row and then parentheses A. Okay, so let me do a quick example so we can get a feel for, well, what do we mean by taking combinations of the rows? So like, what do we even mean by the rows and looking at them as vectors? So if I have this matrix A, we can think of the rows as being vectors. So let me just write row vectors. What are the row vectors of this matrix? So for example, the first row, I can think of it as a vector, as a row vector, and I write that as a row. So I'll put 1, and then 0, and then -2, and then 3. Usually the convention is when we write a row vector, we put a parentheses around the endpoints. If we put a bracket, it's technically fine. This is usually just the convention. It's the convention that the book uses. It's also common to write these as column vectors. So these are the entries of the row. Sometimes if we want to, we can write this as a column vector. So I could have written 1, 0, -2, and 3, just in a regular column vector format that we're used to. But if we do that, we just want to keep in mind that, oh, this is the vector that sort of refers to the first row. Okay, so if I did this for the other rows, the second row would be -2, 0, 4, -6, that's the second row vector. The third row vector would be 5, 2, 1, and 4. Okay, so when we take the linear combinations of the rows to form the row space, notice it's going to be a subspace, just like the null space is a subspace and the column space is a subspace. But the row space is going to be a subspace of Rn. And the reason why it's Rn is because the rows have, if I think of A as being, well, we said A was an m by n matrix. The rows have n entries in them. Because my matrix has n columns. We said it has n columns here. So that's why the rows are vectors that are in Rn. This was in Rn. In my example, it's R4. Because this matrix is a 3 by 4 matrix. Okay. So another way that we can think about the row space is noticing that talking about the span of the rows is the same thing as forming A transpose and talking about the span of the columns in A transpose. So let me just draw that. Let me just write it out so we can see it. If I form the transpose of this matrix, that interchanges the rows and the columns. So the first row of A becomes the first column of the transpose. So I'd get 1, 0, -2, 3 as the first column. The second row becomes the second column, so -2, 0, 4, -6. And then the third row becomes the third column, so 5, 2, 1, 4. So if we take the columns, if we look at the column space of this matrix, the span of these columns, well, that's the same thing as saying we're taking the span of the rows in the original matrix. And that's what this statement says. Okay, so next I want to state a theorem about the row space, which is, if you have two matrices that are row equivalent, then the row space of the matrices is the same. So why is this true? It has to do with what row operations do to the row space. So when we do row operations, what that amounts to, what that's the same as, is what we're doing is we're taking linear combinations of the rows. And when we do that, when we take linear combinations of the rows, that doesn't change their span. It doesn't change the span of the rows. Like if I take linear combinations of the rows we already have, we're not going to somehow get a new independent direction. We're also not going to get rid of directions that we already have. So when we do row operations, it's not changing the span of the rows. That's why the row space of A and the row space of B are equal whenever A and B are row equivalent. Okay, so next I want to state another theorem. So another theorem that's going to tell us, well, how do we find a basis for the row space? Okay, so here's the theorem. Okay, so if A is row equivalent to B, and B is an echelon form, then if I want to find a basis for the row space of A, and it turns out if I want a basis for the row space of A, based off of what we know here, well, that's going to be the same as a basis for the row space of B, because we know that the row space of A and the row space of B are equal based on our earlier theorem. What we do is we take the pivot rows of B, of the echelon form. So it's really important that we're taking the pivot rows in the echelon form, not the original matrix. It's the echelon form. So this is the opposite of the column space in a sense. In a column space, to find a basis, we took the pivot columns, but in the original matrix. With the row space, it's got to be the echelon form. So next I want to do an example, and after we do the example, I'll talk a little bit about why. Okay, so here is the example. Let's say we want to find a basis for the row space of A, where A is this matrix. So this is the same matrix that I had written down before. I've just gone ahead and row reduced it to echelon form. So first what I did is I tried to zero out this -2 and the 5. So those are the first row operations that I did. And after that, I got a row of all zeros. So I switched the second and the third rows so I can get it in echelon form. So this is now in echelon form. And once it's in echelon form and I see where the pivots are, and they're the 1 and the 2, I'm ready to write down my basis for the row space. So the basis for the row space, so for row of A. So let's remember, that's the pivot rows of an echelon form. So we're looking at the pivot rows, but in the echelon form. Okay, so it's the first row and the second row in the echelon form. And I'm going to just decide to write them as column vectors. So the first row as a column vector is 1, 0, -2, 3. And then the second row as a column vector is 0, 2, 11, -11. But if we wanted to write these as rows instead of in this column format, that would also be fine. So I mentioned earlier that I would talk a little bit about, well, why can we not just take the pivot rows in the original matrix? Why did we have to do it in this reduced form? So if we were to look at the first 2 rows of A, of my original matrix, so this matrix right here, notice that the first 2 rows are definitely not going to be a basis for anything. And they're not going to be a basis for the row space of A. Can you see why? Can you see why they would definitely not be a basis, those first 2 rows in the original matrix? They're not going to be a basis because those 2 rows are multiples. They are multiples. And when vectors are multiples, they're definitely linearly dependent. So if they're linearly dependent, they definitely cannot be a basis. Okay, so why did that happen? What's the reason for that? So the general reason for that is, when we do row operations on a matrix, they can change what are called the linear dependence relations of the rows. So what I mean by linear dependence relations of the rows is which rows are linear combinations of the others. That can change when I do row operations. So specifically, if I look at this first matrix, this original matrix A, the first 2 rows are multiples of each other. But over the course of my row operations, oh, and I forgot to mention, the third row is not a multiple of either the first one or the second one. Okay, but when I went from this step to this step, I interchanged the third row and the second row. So the row that had started off being a multiple of the first row now got moved to a different position, to a different row. So by the time I ended in echelon form, the first 2 rows were no longer multiples of each other. So that can happen when I do row operations. And that's the reason why when we find a basis for the row space, we have to look at the pivot rows in the echelon form and not the original.